Hello everyone. Let us try to take some assorted problems on state modeling. Let's look at this problem that we have before us. The closed loop transfer function system is given by CFS to RFS is 24 upon s plus 1 plus s plus 2 plus s plus 3. Determine two different state models. See, this is important. Two different state models. That means the state models are not unique. This is an important point to be noted. So you can obtain different state models. It depends on how you define the state variables. Let us try to obtain the two models. One model using what we call as phase variable method, and we will try to adopt another method wherein we choose canonical variable method. So method 1, okay, by phase variable method. Okay, so the state variables are phase variables. I only hope that you remember this. Otherwise, you need to look into my previous YouTube videos wherein I have solved problems on phase variable method. How to do this? So the given transfer function, we will try to expand the denominator and write the given transfer function. So given C of s to RFS as equal to 24 divided by, we can multiply the three terms here, and what we get is s cube plus 6s square, 5s square plus 1s square, and this is 5s plus 1s, 6s, that is 11s plus 6 is what we get. Alright, so we are able to get the transfer function wherein the denominator is in the polynomial form. Now what do? We will try to cross multiply. Cross multiply. We know this method because we need to get the differential equation in order to have the phase variables defined. Cross multiply and take Laplace inverse. Both the things we will do together. Right? So what do? So we will get s cube into C of s when taken as a differential or Laplace inverse. You will get it as C triple dot plus 6 into C double dot, that is Laplace inverse of a square into C of s, would be 6 d2c by dt square, that is C double dot, plus 11 C dot plus 6c equal to 24r. This is the equation 1. Alright, so equation 1 is the differential equation. So C triple dot, C double dot, C dot, they are all the third, second and first derivatives of C respectively. Alright, where C is the output, R is the input. So we know all these things. So this is a third order differential equation. So how many state variables are needed? Obviously 3 state variables. So 3 state variables are needed to define the system or model the system. So obviously we name them as x1, x2 and x3. So in the phase variable method, what we choose as the first state variable is the output itself. That is x1 is C. This is the first state variable. Alright, so we will call this equation 2. So what do is we differentiate the first state variable, that is x1 dot, and we call it the second state variable, that is x2. And obviously x2 can also be written as C dot for our understanding. This is 3. Alright, and we try to differentiate the second state variable, that is x2 dot, and we call it as x3. This is C double dot. This is equation 4. Now we try to differentiate the x3 dot, and this is nothing but C triple dot. This can be written from equation 1 as minus 6c minus 11c dot minus 6c double dot plus 24r. This is from 1. And now x3 dot can be further written by substituting for C, C dot, C double dot. So what do we get? Minus 6 for C, we will put it as x1 from equation 2. Minus 11 for C dot, we will put it as x2. And minus 6 C double dot, we'll put it as x3. Because on the right hand side of any equation, state equation, you need to have the state variables x1, x2, x3 plus 24. This is equation 5. We are done. We are done with modeling. So from equation 3, 4, 5, so equations 3, 4, 5 in matrix form will give us the state equation. It is so simple. x1 dot, x2 dot, x3 dot, vector equal to the matrix 0, 1, 0. We can write it by inspection if you remember. That is, the last row, first row has got 0, 1, 0. The second row is 0, 0, 1. The third row is the negative of the coefficients taken in this order. That is minus 6, minus 11, minus 6. This whole thing, even from this equation, minus 6, minus 11, minus 6. So this is x1, x2, x3. And there is no r term in the in the equation number 3, that is 0. In equation number 4, there is no r. Equation number 5 has got 24r. The whole thing into r. This is our state equation. Alright. State equation is of the form x dot equal to x plus bu. So simple. We can identify the state matrix A and the input matrix B from the given equation. Now what is the output equation? Look at equation 2. It is giving me the output equation directly. Output equation from equation 2, what can we say about C? C is nothing but the output. That is equal to x1. In the matrix form, we can write this as 1x1, no x2, no x3 multiplied with the state vector x1, x2, x3. This is my another equation. We will call the 6, the 7. What is this equation 7 called? It's the output equation. Alright. So, equation 6 and equation 7, equations 6 and 7 completes the modeling. In what we call as, rather using phase variable form, using phase variables with matrix A or state matrix in companion form. This is an important form, companion form. So this completes modeling, one modeling. We will arrive at the second model, okay? This is model number 1. Now we will try to do model 2, second model. Model number 2. How do we do this? Model number 2, we will try to see the given transfer function as partial fractions, and we have done this also, the canonical form. So we will try to do. This is 24 divided by s plus 1 into s plus 2 into s plus 3. So the given transfer function is written with the denominator in the factorized form. So we will try to write this as a upon s plus 1 plus b upon s plus 2 plus c upon s plus 3. Alright. So what we have done is the partial fraction expansion. We will call this one. This is by partial fraction. What do we know next? We try to find these residues. So we will try to adopt Heaviside expansion. We will try to evaluate A as equal to s plus 1 into the given transfer function c of s to r of s. Evaluated, s is equal to minus 1. This comes out to be 24 divided by s plus 2 into s plus 3. Careful evaluation. S is equal to minus 1 would be 24 by 2. That's equal to 12. Now we will evaluate b. b is evaluated as the denominator of b into the given transfer function, that is s plus 2 into c of s to r of s, evaluated at s is equal to minus 2. So this would be 24 divided by s plus 1 into s plus 3. This would be 1 and 1, and this will be minus and minus 24. Okay, c equal to s plus 3, the denominator of c, multiplied with r of s to c of s, means rather c of s to r of s, c of s to r of s, evaluated at s is equal to minus 3. That will be 24 divided by s plus 1 into s plus 2. This comes out to be 24 by 2. I see it as 12. Alright, so we have evaluated ABC. So what do we do further? So we'll put it in equation 1. Substituting in equation 1. What do we get? We get c of s to r of s as equal to 12 divided by s plus 1 minus 24 divided by s plus 2 plus 12 divided by s plus 3. What do we do further? We will cross multiply. R of s, we will take it to the right hand side. C of s is 12 divided by s plus 1 into r of s plus minus 24 divided by s plus 2 into r of s plus 12 divided by s plus 3 into r of s. This is the equation 2. Okay. What do we do? We will try to identify, we will call, let x1 of s equal to 12 into r of s divided by s plus 1. We will cross multiply. Cross multiplying. What do we get? S into x1 of s plus x1 of s equal to 12 into r of s. We will try to take this x1 onto the other side and take Laplace inverse. Taking Laplace inverse. What do we get? This would be x1 dot equal to minus x1 plus 12 into r. This is the equation 3. Now similarly we will do with the other things. We will identify the second term, that is x2 is identified as x2 of s is equal to minus 24 divided by s plus 2 into r of s. So we will do the same thing, cross multiply and Laplace inverse. Multiply and take Laplace inverse. What do we get? We get it as s into x2 of s, Laplace inverse is x2 dot equal to minus 2x2 minus 24r. This is the equation 4. Alright. The third one, that is the third term in equation 2, is identified as x3 of s. That is 12 divided by s plus 3 into r of s. Again the same thing, we will do cross multiply and inverse. Cross multiply and take Laplace inverse. What does it yield? We get it as x3 dot equal to minus 3x3 plus 12 into r, equation 5. Look at equation 3, look at equation 4, equation 5. Is it not in the required form? They are in the required form. In the matrix form, equations 3, 4 and 5 in matrix form. We'll put them in matrix form. We get this as x1 dot, x2 dot, x3 dot, right, equal to, get minus 1x1, no x2, no x3. The second equation, no x1, minus 2x2, no x3. The third equation, no x1, no x2, minus 3. This is into x1, x2, x3 plus. First equation we have 12 minus 24 plus 12 is the state equation. Alright, because it is in the form x dot equal to ax plus bu. V into u. Alright. So look at matrix A. This is in the diagonal form. You have got elements along the diagonals, and these elements are nothing but the poles of the system. That is minus 1, minus 2, minus 3 are the poles of the system, and this is the diagonal form. Right? We will write the output equation also before we conclude. So we will look at the equation 2 from equation 2 we can write C as equal to x1 of s plus x2 of s plus x3 of s. Or in other words, with Laplace inverse, it becomes C into x1 plus x2 plus x3 in time domain. If we put it in vector matrix form, output C is nothing but 1, 1, 1, x1, x2, x3. So this is the output equation. So this is equation 6, equation 7. Equation 6 and 7 would complete the modeling. Equation 6 and 7 completes the modeling in the state space. So interestingly, matrix A is in the diagonal form or canonical form. Hence, these variables, the choice of these variables are called canonical variables. Okay? So we'll try to have a recap. I have to take one page at a time. Okay, so This completes the modeling problem. So we have done the modeling in two different ways.